Hello everyone and welcome back to Introduction to Logic. Just a quick video this week as we are closing things out. We're just learning a few new proof rules that are actually supposed to make your life a bit easier. Right? Most of them that we're going to learn this week, in fact maybe all of them, allow you to avoid making a certain assumption, maybe even more than one. Right? So let's jump right in to these new rules. Okay, so we have on the order today disjunctive syllogism, modus tollens, double negation elimination, and De Morgan's. So let's jump in. Disjunctive syllogism, as you can see in the name, disjunctive, works over disjunctions, right? Or. The symbol means or. So if we have a disjunction like this, P or Q, and we know that one side of it is false, we know that the other side must be true. That's disjunctive syllogism. Why does it work? Because for a disjunction to be true, at least one side has to be true. Thus, if I'm asserting my premise is true, and I also know that one side of that disjunction is false, well, the only way for both of those claims to work together is if the other side is true, right? So it's just a matter of necessity. Okay, so worked in a proof, it will look something like this. Let's build in a little more complication than what we have on the left. Let's say P or Q and R. And we know not P, and so we're trying to derive Q. All right, so step one, let's put our premises down. P or Q and R. Premise two, not P. So using disjunctive syllogism, I can see I have a disjunction with P in it as my first premise. And premise two says that P is false, which tells me the other side has to be true. I say DS, right? DS for disjunctive syllogism. I cite the disjunction first, then the negated disjunct second. Okay, and then to get my conclusion is pretty simple. That's just conjunction elimination, line 3. Okay, not too bad. If you didn't have disjunctive elimination, disjunctive syllogism, you would have to do a bit more footwork to get to the same conclusion. Okay, let's get this out of the way and move on to modus tollens. When we do practice problems at the end here, you'll get to see all of these together. So modus tollens, or MT, sounds a lot like modus ponens, right? Well, that's because they both work on conditionals, but in a different way. Okay? So we have a conditional, like if P then Q. Modus tollens requires that we have the opposite of the consequent. That's the right side. If we have that, then we can derive the opposite or the negation of the left side. So why does this work? Well, if P were true, then by premise 1, Q would have to be true. So since we know already that Q is false, there is no way for P to be true. If it were true, it wouldn't be possible for Q to be false already, right? Okay, so let's build in a little more complication and see what it looks like in a proof. If P, then Q and R. It's not the case that Q and R. So prove not P. Step 1, let's get our premises here. In Q and R. It's not the case that Q and R. Okay, so this is going to be a one-line proof, right? You can see in this conditional, I have this conjunction as my consequent. And here in premise 2, I have that same thing, but there's negation symbol applied to it. Well, when you have that, you know that the left side of that conditional has to be false, not P. Using modus tollens, cite the conditional first and the negated consequent second. Okay? Simple as that. Now this one saves you about 3 lines. It kind of depends, but usually it saves you about 3 lines. If you didn't have this, let's see, move this over here. What would your proof have looked like? In fact, we can just use the same thing here. What would your proof have looked like? Well, we would have had to start with an assumption of P, then use conditional elimination 1 and 3 to get this, which introduces a contradiction, negation elimination 2, 4. Finally, on line 6, we get to say not P, negation introduction 3 through 5. Right? So this is what the SAM proof looks like without access to Modus tollens. You can see that Modus tollens save you a good bit of headache here. All right, let's move on to double negation elimination. This is a pretty simple rule. Double negation elimination, we write D in E. Just says this: if you have 2 negation symbols next to one another, you can delete them. So not P is equivalent to P. Why? Why does this work? Well, think back to truth tables. The negation symbol just flips the truth values of whatever it's applied to. So if you flip again, given that there's only true and false, they're going to end up, a not P is going to end up saying the exact same thing as P. So that's the double negation elimination. You can also do double negation elimination in cases like this. But note that it gets rid of 2 and only 2 negation symbols at a time. So you would end up with not P. Okay? You could use it when there are 4 negation symbols, but you can only get rid of 2 at a time. So you would need yet another step if you wanted to show that not P was equivalent to P. Okay? Now, you cannot use it when it's like this, right? Even though, technically speaking, like if you did a truth table, this would end up showing the inference rule won't apply here because the parentheses don't allow it. The negation symbols need to be touching. Okay. All right. So suppose you have the following argument: P and not Q, and we want to prove that P and Q. Okay. So P and not Q is our only premise. We're going to need to start by breaking apart this conjunction. So let's do that. Conjunction elimination, line 1. Now that we've done that, we can transform not Q using double negation elimination. All you do is cite the line you're transforming. And we can build that conjunction back together. P and Q, conjunction introduction, 2, 4. Okay? Not too bad. All right. The next rule is not necessarily difficult, but also not as intuitive. De Morgan's. Technically speaking, there's 4 ways you could use De Morgan's, but there's really only 2 patterns, so we'll break it into 2. De Morgan's works over conjunctions and disjunctions that have some kind of negation involved. So for example, you can transform this claim into this. These 2 things say the same thing, right? Why? Well, P and Q tells us that both P has to be true and Q has to be true, right? They both have to be true. So if I'm telling you that's false, it's not the case that P and Q. I'm telling you that, well, one of P or Q is false, or maybe even both of them are false, right? One is false or both. And if you look at what we have, the expression we have on the right, it's not the case that P or it's not the case that Q. That's exactly what that says. Okay? It says, look, P might be false, Q might be false, at least one of them is, and maybe both of them are. So they say the same thing, logically speaking. Further, if you know that P or Q is false, not P or Q, then you know not P and not Q. Okay? So these are the two forms. The way that I typically recommend you remember how these work, if you encounter a conjunction or a disjunction that are within parentheses like this and negated on the outside, just know that you can flip the symbol, right? Up becomes down and down becomes up. And you can move the negation symbol in to the individual terms. So all we're doing is flipping the symbol and moving that negation symbol inwards. Right? That's how both of these things work. Now, you can also transform from the right side to the left. So you can transform this into this. It's symmetrical. Right? You can do both. So if you find yourself with a disjunction like this one, where both of its terms are negated, like this one, know that, once again, you can flip that symbol, right? So down becomes up and up becomes down. And you can move those negation symbols out from the individual sentence letters and behind a parentheses like this, okay? So it's just kind of a pattern that you really have to get used to, right? There are like the flipping the symbol and distributing the negation is helpful, but really you just need to learn the pattern. Okay, let's move this over here and do some practice. Let's say we know if P, then Q or R, and we know that not Q and not R. Okay? And we want to prove not P. Okay. Step one, let's get our premises. If P, then Q or R, not Q and not R. That's 1 and 2. So the first thing I notice once I'm looking for this pattern of De Morgan's, I see, oh, look, I have this, right? Not Q and not R is that same pattern, which means I can transform it into this, okay? So I'm going to do that. It's not the case that Q or R. So what did I do? I flipped the symbol, right? Up became down. And then I moved these negation symbols away from the sentence letters and outside of a parentheses. Okay? And all I say is De Morgan's, D-E-M, and the line I transformed. That's it. Okay, but I'm trying to get not P. That's not getting me there immediately. But now notice that my consequent here, the right side of my conditional, is the opposite of what I have on line 3. That means I get to use one of our new rules, not P, using modus tollens 1, 3. Okay? So if we didn't have these new rules, this would take quite a lot longer to prove, right? I would have to assume, I would begin by assuming Q or R. I would show that that assumption led me to a contradiction. And in order to do that, I would have to use disjunction elimination. So that's another assumption. Once I had shown that that led to a contradiction, I could say, oh, so it's false that Q or R. And then I could use modus tollens, right? Okay. So let's move on to another example. Sorry. Suppose we know P or Q and R. Not Q or not R. And we want to prove P. This is going to be similar, except now we have a disjunction in premise 1 instead of a conditional. Not Q or not R. Well, again, once you're used to De Morgan's, you see these patterns pretty quickly. I see this on line 2. is this pattern, which means I can transform it into this, right? So step one, I'm going to flip the symbol. Down is going to become up, right? Step two, I'm going to remove those negation symbols from my sentence letters. So I'm going to get Q, R, and then I'm going to put the negation symbol behind parentheses. That's De Morgan's 2. Now, I see that premise 1 has my line 3, but my line 3 is negated. Okay, well, when we have that situation for a disjunction, we know that the other side of the disjunction has to be true. That's disjunctive syllogism 1, 3. Okay? So De Morgan's is not that difficult to employ. It just might take a little practice for you to start recognizing it, right? For you to start seeing the pattern. But you only have to cite one line, right? It's not too difficult to employ. Let's now do some practice problems from the book so we don't know what to expect beforehand. Okay, so I am in chapter 18 of our textbook for all X, and I'm going to skip down to section B. Section A contains already solved problems where they are asking you to fill in the missing information. That's very good practice. But let's move down to section B. Section B begins, problem 1, with E or F, F or G, not F, therefore E and G. Okay, so first thing I notice is that my conclusion is a conjunction. When that happens, not always, but when that happens, it's a good idea to look and see if you can prove the individual elements as well, right? Because if I can prove E and I can prove G independently, well, I know I can join those two things together with a conjunction introduction, right? So I'm looking now to see if I can get E and G by themselves. And then I can bring them back together. And I notice that I've got E appearing here. I've got G appearing here. Both are bound by disjunctions. Okay. So how do I get rid of a disjunction symbol? Well, before today, our only rule for doing that was disjunction elimination, which requires 2 assumptions, right, for each time. But now we have disjunctive syllogism, which also gets rid of a disjunction. But the catch is, in order to use disjunctive syllogism, we need to show that one side of that disjunction is false. So can we do that? Well, yeah, not F is one side of both of these. So that's how I'm going to end up getting E and G, right? That's how I'm going to end up getting both of them. So let's work it. All right, so I have E or F, I have F or G, and I know not F. 1, 2, 3. Step 1, disjunctive syllogism over line 1. So I know E has to be true. Disjunctive syllogism, 1, 3. Again, I'm allowed to do that because I have a disjunction here, and I know that one side of it's false. That means the other side has to be true. I'm going to do the same thing, but with the disjunction on line 2 this time, to get that G must be true. Disjunctive syllogism, 2, 3. Would you look at that? I proved E and G by themselves, and now all I have to do is bring them together. Conjunction introduction, 4, 5. That's a pretty simple one. Okay, how about we keep it? Let's move it here. Number 2. Number 2 looks like it might be a little more complicated. It says only one premise, M, or if N, then M. Conclusion, if it's not the case that M, then it's not the case that N. And this is going to be a little bit more complicated because it revolves around one of our old rules that requires assumptions, sorry. But it's not going to be too bad. Line 1, our premise, M or if N, then M. Now, let's briefly talk proof strategy. Our conclusion is a conditional, right? With conditionals, you should always follow these two steps. Step one, look to see if your exact conditional appears in the premises. Like you can just get it out by using conjunction elimination or something like that. If you cannot, if it does not appear exactly as it does, then we're going to need to make an assumption for the purposes of conditional introduction. The assumption you want to make is the left side of the conditional you're trying to prove. So we're going to need to start by assuming not M. Okay? Start by assuming not M. And we want to show that having assumed the left side, not M, we can get to the right side, which is not N. So that's our goal. Now, is there anything I can do with not M at this point? Yes, now that I have my new rules, I can get if N, then M. How? Well, line 1 is a disjunction, and one side of that disjunction is M. Since I'm assuming now on line 2 that that's false, the other side of that disjunction has to be true. That's disjunctive syllogism 1, 2. Okay? Now I get to use another new rule. If N, then M. Well, I know, again, M is false. So N has to be false, right? And that is modus tollens 3, 2. So I arrived at what I wanted. Now I get to come outside of this assumption. I get to say, if you assume not M, then you can arrive at not N using conditional introduction. Cite the entire subproof 2 through 4. Not too bad, right? Okay, let's move on to problem 3. M or N and O or P. If N, then P, not P. Therefore, M and O. Okay, so let's get our premises down and we'll talk proof strategy again. This first premise is a bit long. M or N and O or P. If N, then P and not P. Okay, 1, 2, 3. So let's talk proof strategy. I see that my conclusion, again, is a conjunction, which tells me, again, I might be able to get the whole thing all at once, but it's also going to be totally fine if I can only prove M at one time and then O at another time, because I can join them together using conjunction introduction. So it looks like that's what I'm going to have to do. I don't see anywhere where M and O are already joined together. I'm going to need to prove them individually. So first up, can I get M by itself? Well, the only place M appears is up here. And there's a problem. One, it's part of a disjunction, okay? And two, that disjunction is bound by a conjunction. Now, we know that conjunctions are easy to break. Really, all you have to do is ask it to break, and it does, right? A conjunction elimination will get rid of this and get M or N by itself, okay? But in order to get M from that, I'm going to need to show that N is false. That would allow me to do disjunctive syllogism in order to get M. So can I prove that N is false? That's my new goal. Can I prove that N is false? Well, yeah, I can. N appears here as part of a conditional, and I see on line 3 that the right side of that conditional is false, which means, using modus tollens, the left side has to be false. Okay, great. I've got a path for M. What about O? O is going to be the same thing, just a little simpler. I'm going to break that conjunction apart so that I just get O or P. And look, I have not P here. So I know that O is going to have to be true. So this one's pretty straightforward. It just looks like it might be a little more complicated. Let's show you how this works. First up, I'm just going to break apart premise 1 to get that done. Conjunction elimination 1. O or P, conjunction elimination 1. Okay. Next step, I'm going to use the modus tollens that we discussed to get not in. That's modus tollens from 2 and 3. Now that I have that, I know that M must be true using disjunctive syllogism 4, 6. Now I need to work on O, right? I've got M, but now I need O. Well, as we said, we have O or P here, and we know that P has to be false, so that means O has to be true. Again, that's disjunctive syllogism, this time 5, 3. And now all that's left is to bring them together. M and O, conjunction, introduction, 7, 8. Okay? Not too bad. It just requires usage of our new rules multiple times. All right, there's one problem left, so we might as well work this one. It looks longer. Number 4. X and Y or X and Z. It's not the case that X and D, D. D or M, prove M. Okay. Interesting. Now, how are we going to do this? Well, M appears only once in our premises, and it's part of a disjunction. So what is likely going to end up being necessary is that we can show that D is false, right? We need to show that D is false. Okay. All right. In order to use disjunctive syllogism. So let's get our lines here. X and Y or X and Z. Not the case that X and D or M. 1, 2, 3. Okay, so the first thing that I notice is that I have a conjunction that could be transformed using De Morgan's. So I'm going to go ahead and do that. More information is better than less information, right? So that's going to be not X or not D, okay? Not X or not D, using De Morgan's 2. Okay, so now we have not D here. We want that to be true so that we can use our disjunctive syllogism. But how can we get that? We can only get that if we can show that X is true, right? If X is true, then not X is false. And so not D must follow from that using disjunctive syllogism. Can we show that X is true? Yes, we can. Look on premise 1, we have a disjunction that says X and Y or X and Z. Notice that no matter which side of that is true, X is going to end up being part of it, right? So unfortunately, what we're going to have to do here is make an assumption, a couple of them, because we need to do disjunction elimination now. So I'm going to start by assuming the left side of my disjunction, that's X and Y. It's going to be a pretty simple one though. And then I'm going to show, hey, look, X follows from that using conjunction elimination, line 5. I'm going to begin my other assumption of the right side of this disjunction on line 1. And look, X also follows from that. Conjunction elimination, this time line 7. So on line 9, I get to say that X must be true from disjunction elimination 1, 5 through 6, and 7 through 8. Great. Now I have X. Okay. Well, if I have X, since that is the opposite of not X, I can now do my disjunctive syllogism to get not D. We'll talk about how in just a second. 4, 9. Okay, so remember, disjunctive syllogism works like this. If you have a disjunction and you know that one side of that is false, the other side has to be true. That also works if you have something like this. It's not the case that A or B, and you know A. Well, A is the opposite of not A. So you can also use disjunctive syllogism in these cases. Okay? All right, get rid of this. That's exactly what we did here to get D. Notice that on line 4, we have X or not D. On line 9, we have just X. That's the opposite of the left side of the disjunction. Now that I have not D, I can use disjunctive syllogism again to get M. How? On line 3, I know that D or M. D or M. And if I now know that D is false, M has to be true. Disjunctive syllogism, 3, 10. Okay. So that was a bit more difficult than the first 3 we worked. But overall, not too bad. It just required the use of disjunction elimination, which is honestly one of the harder rules to get used to. But the key here was spotting that first De Morgan's, right? This De Morgan's makes premise 2 useful, right? It allows us to eventually do this disjunctive syllogism. Without that De Morgan's, you're not going to be able to use the disjunctive syllogism. Without this De Morgan's, we're looking at many more assumptions than the ones we made here. You would have to assume not X in order to show that that leads to a contradiction, right? If you had began instead of that De Morgan's by assuming not X, then you could do your disjunction elimination where you assumed X and Y. You got X, oh, that's a contradiction. You could show that both sides lead to the same contradiction and then get X by itself. Okay? You could get X by itself that way. But that's still not going to help you until you do the De Morgan's, right? So it's very useful. De Morgan's laws are extremely useful. Okay, well, that's all that we're going to be covering for this class. Do note, however, that logic is massive. We have barely scratched the surface here. Right, we've covered most of the rules that you see in ordinary systems for TFL, truth functional logic. But there are still a handful of rules we didn't discuss that other systems use, like hypothetical syllogisms, etc. You can prove any valid argument currently with the rules we have, though. Our system is complete. You don't need any other rules. Just some systems have a few extra. But there's many other kinds of logic too, other than truth functional logic. You can start building in more complexity by building in classes and possibility and necessity. Maybe you might even be interested in considering whether logic should have more than just true or false. Or maybe you're interested in exploring many-valued logic, where you have at least 3 values, true, false, and indeterminate. There's a lot more to do in logic than just what we've covered. But at the end of this class, you should at least have the basics to get going. Okay? So it's been fun. I hope you think so too. But that's going to be it for today.